For anyone working in quantitative modeling, there is this constant, almost existential battle.
Oh, absolutely.
Right. Because on one side, you have the elegant precision of a scalpel, closed-form parametric models.
Right, the analytical baseline.
Exactly. They're computationally efficient, mathematically beautiful, and, well, if the market behaves exactly the way your underlying equations assume, they're practically unbeatable.
Yeah, but that's a massive if, right? Because on the other side, you have the robust adaptability of machine learning.
Yes, the heavy machinery.
Right. Non-parametric methods are flexible, entirely data-driven, and quite frankly, they just do not care about your rigid structural assumptions.
They really don't. And that tension, that exact trade-off, is the core of our deep dive today.
It's the defining problem of modern quantitative finance. You are constantly weighing computational efficiency against, model-agnostic adaptability.
Right. And knowing your background and the background of everyone listening in machine learning, data science, and pure mathematics, we are skipping the introductory fluff today.
Let's get right into it.
We are getting straight into the mechanics of a May 2026 paper titled Volatility Modeling in Markovian and Rough Regimes, Signature Methods and Analytical Expansions.
It's a fantastic paper.
It really is. Our mission here is to dissect how the authors construct and contrast two very rigorous methodologies for calibrating implied volatility surfaces.
And the dichotomy they present is an incredible case study. First, they establish a highly accurate analytical baseline, focusing specifically on the Markovian Heston model and the non-Markovian rough Bergomi model.
That's the scalpel.
That is the scalpel. And then they contrast that baseline with a highly flexible, non-parametric approach that utilizes rough path theory and the truncated signature of a primary stochastic process.
So we're going to look closely at the mathematical mechanics, the underlying algebraic structures, and the actual numerical realities of operating in both paradigms.
That's good.
Let's start by setting up that analytical baseline, because to really appreciate the necessity of the machine learning approach later, I feel like we have to understand the sheer elegance of what it is competing against.
Oh, for sure. So the paper briefly revisits a known second-order asymptotic expansion for the Heston model.
Right, which involves solving a system of nonlinear equations for your standard parameter.
Exactly. But the real heavy lifting on the analytical side is a newly proposed closed-form calibration for the rough Bergomi model.
And calibrating rough Bergomi is notoriously difficult.
It's a nightmare.
Yeah.
Unlike standard stochastic volatility models, its volatility is driven by a Volterra-type fractional Brownian motion.
Right.
Because fractional Brownian motion is not a semi-martingale, and it completely lacks the Markov property, you are dealing with a process that has memory.
So the standard PDE approaches
They just don't work. The mathematical framework doesn't allow for the PDE methods you might use in a typical Markovian setting. So the authors develop a highly efficient VIX-based calibration scheme.
And it relies almost entirely on short maturity option information to lock down the parameters analytically, right?
Yes, it's a four-step cascade.
The logic they use to extract those unobservable parameters is just fascinating to me. Instead of throwing an optimizer at the whole surface, they target specific geometric features of the implied volatility.
Right. They isolate the variables perfectly. Like for step one, they go after the Hurst index, the parameter that dictates the roughness of the volatility. They find it by looking directly at the skew of the implied volatility smile. If you take reference strikes symmetrically on either side of at the money, the difference in those implied volatilities isolates that skew.
And the Hurst index just falls right out of the asymptotic.
Exactly. It's brilliant. And they apply that same philosophy for step two to extract the volatility of the volatility process itself.
The vol.
Right. To find that parameter, they analyze the short-time behavior of VIX options. Specifically, they look at the money implied volatility as the time to maturity approaches zero.
I actually want to pause on the physics of why that works.
Sure.
Why does shrinking the time to maturity isolate the volatility of volatility?
Well, think about what happens as that time window collapses to zero.
Right. The slower macroscopic effects like mean reversion or the drift of the underlying asset, they just don't have time to materialize.
Exactly. The noise of the broader market dynamics essentially fades out,
leaving you with the pure, instantaneous diffusion of the variance process itself.
That is exactly the mechanism. It relies on a rigorous asymptotic property of the VIX implied volatility that mathematically isolates that diffusion parameter.
That makes total sense. So what's step three?
Step three is extracting the correlation parameter. Once they have the Hurst index and the vol, They evaluate the short-time skew of that same at-the-money implied volatility.
And they apply a finite difference scheme to the derivative with respect to the log strike, right?
You got it. And finally, step 4. They run a regression of at-the-money options across different maturities to solve for the initial volatility.
Utilizing that known asymptotic relationship, where the implied volatility scales linearly with time to the power of twice the Hurst index.
Exactly. It cascades perfectly. You solve one parameter, feed it into the next equation, and reconstruct the entire rough Bergomi dynamics practically instantaneously.
But, reading through this, I kept hitting a conceptual wall.
Oh, really? What was it?
If the mathematics here are so tight, and we can calibrate rough Bergomi so neatly using this short maturity cascade, why abandon it? I mean, why do we need to introduce the massive computational overhead of rough paths and machine learning at all?
It comes down to the fragility of parametric assumptions.
Okay, expand on that.
Well, the analytical method is mathematically beautiful, sure,
Mm-hmm.
but it is deeply brittle. It fundamentally assumes the market is perfectly, flawlessly described by that specific fractional Bergomi structure.
And real markets never are.
Never. Real market data exhibits highly anomalous stylized features. You have jump dynamics, unpredictable macroeconomic shocks, and complex temporal dependencies that just do not fit neatly into a Volterra kernel.
Right.
When the market steps outside of those specific structural assumptions, the analytical model simply shatters. It cannot adapt.
So you are forced to abandon the neat equations.
Exactly. You have to adopt a model-agnostic, data-driven framework that can actually learn the dynamics directly from the noise.
So the transition isn't just for the sake of using machine learning. It is an absolute necessity if we want to describe market chaos mathematically.
Precisely.
And that takes us straight into part 2, the mathematics of signatures and rough path theory.
This is where it gets really interesting.
Because parametric forms limit our flexibility, the authors propose modeling volatility dynamically as a linear functional of the signature of a primary stochastic process.
Right. And to process how they do this, we need a rigorous definition of what a signature actually is.
Let's lay it out for the listeners.
So in rough path theory, the signature of a path is an infinite sequence of its iterated integrals. And these integrals are naturally organized into an extended tensor algebra.
Okay, so geometrically, how should we conceptualize that?
You could think of the first level of the signature as the basic increments of the path. Then the second level captures the area bounded by the path.
The third level captures the volume.
Exactly, and so on, scaling up into higher dimensional geometries. It takes the sequential temporal features of a stochastic path and encodes them into a very rich, highly structured algebraic object.
And to manipulate these algebraic objects, the paper relies on an operation called the shuffle product.
Yes, the shuffle product is key here.
The authors actually cite a really helpful analogy for this, which I loved. Evaluating the shuffle product of two tensors is exactly like shuffling two decks of cards together.
That's a perfect way to visualize it.
You interweave the cards in all possible combinatorial ways, but the critical rule is that the relative internal order of each individual deck remains totally intact.
Right, and that internal order preservation is what makes the algebra actually work. The shuffle product allows us to combine two tensors while respecting the temporal sequence of the underlying integrals.
Which leads directly to Chen's identity, right?
Yes. Chen's identity allows us to concatenate paths, but even more importantly, it leads to the group-like property of the signature.
Okay, break that down. Why is the group-like property so important?
It is arguably the most powerful tool here. It states that evaluating the shuffle product of two tensors on the signature is mathematically equivalent to evaluating each tensor separately and then multiplying the resulting scalars.
Wait, let me make sure I'm mapping the implications of that correctly.
Go for it.
If we can convert the multiplication of two signature evaluations into a single evaluation of their shuffle product, we are essentially linearizing polynomials.
Yes, exactly.
Instead of dealing with highly nonlinear products of iterated integrals, which are notoriously difficult to optimize, the shuffle product maps them into a linear combination of higher-order signature elements.
We are turning a complex nonlinear problem into a high-dimensional linear one. That linearization is the holy grail for this kind of modeling.
But of course, applying it to financial data introduces a severe mathematical hurdle.
Naturally. There's always a catch.
Standard Riemann-Stieltjes or Young integration theories work perfectly fine if your path has bounded variation, or at least, a Holder continuity strictly greater than 1/2.
Right, but stochastic processes in rough volatility regimes, like fractional Brownian motion, have a holder continuity less than or equal to 1/2.
The paths are just too jagged.
Exactly. The classical integration sums simply fail to converge.
The market moves too violently for classical calculus to handle.
Precisely. And this is where rough path theory finally intervenes. To integrate against a path with such low regularity, you have to lift the path into what is called a pre-rough path.
Meaning you compute and store exactly enough levels of iterated integrals, specifically up to the integer floor of the p-variation, to uniquely capture the path's roughness.
Yes. Once you establish those foundational lower-level integrals, a principle called the extension theorem kicks in. It guarantees that you can uniquely and safely extend the functional to all higher levels in the tensor algebra without hitting those convergence issues.
Okay, wait a minute. I am thinking about the underlying geometry of the signature map here.
Okay, what's undermined?
The signature captures the geometric shape of the path, the sequence of movements in space, but it is entirely invariant to reparameterization.
Right. Tree-like equivalence.
Exactly. It suffers from tree-like equivalence. So if we lose the parametrization, we completely lose the concept of time.
They do.
So a market crash that happens in 2 seconds would have the exact same spatial signature as a slow bleed over 2 months. We cannot possibly price time-dependent options or use the Stone-Weierstrass theorem if our model cannot perceive time.
That is a phenomenal observation, and it highlights a critical technical gap that the authors absolutely have to bridge.
So how do they fix it?
To recover that timing information and ensure the signature map is injective, they introduce a deliberate intervention: time augmentation.
Time augmentation, okay.
They add time as an explicit, strictly increasing coordinate to the primary stochastic process. So instead of just computing the signature of the spatial path, they lift the augmented path, which is the vector of time, and the spatial path.
Oh, it's like looking at a GPS tracker.
How so?
If you only have the spatial route on a map, you know I went from my house to the bank. But without timestamps on those coordinates, you have no idea if I drove the speed limit or if I was fleeing a bank robbery at 100 miles an hour.
That is an amazing analogy, yes.
Time augmentation essentially stamps the GPS data so the signature captures both the shape and the speed of the path.
That is exactly what it does. By treating time as an additional spatial dimension, they lift the path into a time-augmented, weakly geometric rough path. And the paper references Theorem 3.30, which proves that this time augmentation completely recovers injectivity up to tree-like equivalence. It satisfies the crucial point separation requirement.
And because the points are now separated in the feature space, the universal approximation theorem applies.
Exactly. This formally proves that linear functionals of this time-augmented signature can approximate any continuous functional of the path uniformly well.
Okay, wow. With that functional analysis foundation solidified, we can finally connect the pure math directly to the pricing stochastic differential equation.
Let's do it.
In the paper, they model the instantaneous volatility as a linear combination of the truncated signature. You have a set of learnable coefficients taking the inner product with the elements of the signature, truncated at some level n.
Yes, the modeling step is wonderfully straightforward once the algebra is set up.
Yeah.
But, to price an option, you have to integrate the discounted asset price against this volatility model using Ito's formula.
Right.
Because the volatility term is represented by the signature, integrating it yields an explicit exponential formula for the price process. However, and this is a big however, the Ito integration relies heavily on the squared volatility term.
And squaring the volatility is where the math demands a massive toll.
A huge toll.
Because you are squaring the linear combination, you are inherently taking the product of two signatures. And thanks to the shuffle product identity we discussed earlier, we know that multiplying two signatures translates into a linear combination of even higher order signature elements.
Exactly. This squaring operation defines a matrix, denoted as Q of t, which organizes all these higher order terms. By mathematical construction, this Q matrix is negative semi-definite.
Okay, so what does that give us?
Well, if you take its Cholesky decomposition, the pricing equation suddenly becomes computationally tractable. You can simulate the asset price entirely based on this decomposed matrix and the stochastic integral of the signature.
Which means completely avoiding the need to continuously reevaluate the full nonlinear SDE at every microstep.
Exactly.
But let's pause here and really look at the computational reality of that Q matrix, because the paper details a massive dimensionality explosion.
No, because it's wild.
Let's say you decide to truncate your volatility model at a simple level, like n equals 3. Because of the shuffle product required to compute the squared terms in the Q matrix, you actually need to compute signature terms up to level 2n plus 1.
Right.
So to run a relatively simple level 3 model, you must calculate the signature up to level 7.
And in a time-augmented space, moving from level 3 to level 7 is not a trivial jump.
Not at all. If you have a one-dimensional primary asset process and you augment it with time, you now have a two-dimensional path. The tensor space for a two-dimensional path computed up to level 7 contains exactly 255 dimensions.
Yeah, it scales aggressively.
You are calculating, storing, and fetching entries from a 255-dimensional tensor algebra just to populate a tiny 15 by 15 Q matrix. I mean, the theoretical linearization of the shuffle product is gorgeous, but practically,
It's extremely heavy.
the computational cost of those higher-order cross-terms scales exponentially. It is computationally brutal.
Which brings us to the ultimate proving ground. Part 4. The numerical experiments.
Right, because the pure math only matters if it can survive the computational realities of the optimization landscape.
Exactly. Having built this theoretical engine, the authors evaluate how it actually performs when trained against synthetic market data.
Their experimental setup is very rigorous. To navigate that high-dimensional space, they optimize the model using an LBF-GSB algorithm.
And they apply strict box constraints to prevent the gradients from exploding, which also speeds up convergence.
The loss function they minimize is the least squares error between the model's implied volatility and the target market volatility. But crucially, they weight this loss function by inverse vega.
That's a really smart detail.
It is. It prevents the optimizer from overfitting to deep out-of-the-money options where vega is low and bid-ask spreads are typically wide. It forces it to focus evenly across the surface.
Right. And they train this across 20 option contracts, with maturities ranging from 0.1 to 1.6 years, utilizing 800,000 Monte Carlo paths just to suppress simulation variance.
So how does it actually perform?
Well, they start the benchmarking against the Markovian Heston data. In the uncorrelated setting, where the correlation parameter is 0, the signature method is spectacular.
Really?
Yeah, it matches the analytical approximation almost perfectly, yielding calibration errors around 10 to the negative 4. It successfully learns the linear dependence on the variance process.
But the results shift slightly when they introduce a heavy negative correlation, right? Like negative 0.5.
They do. The analytical baseline maintains its error rate, but the signature method's error creeps up into the 10 to the negative 3 range for certain contracts.
And if you trace the math back to our tensor discussion, the effects of negative correlation manifest heavily in the complex, higher-order interactions between the asset and the variance process. So truncating the model at level 3 simply cuts off the nuance required to capture that deep correlation. But, as we established, pushing the truncation to level 4 to capture it would require computing signatures up to level 9.
Which is computationally overwhelming.
Yeah.
It's a very real limitation of the truncation depth.
Right.
However, the signature model truly flexes its capabilities in the non-Markovian setting.
Yeah.
The rough Bergomi results.
This is where it gets exciting.
For this experiment, the primary driving process is a fractional Brownian motion with a Hurst parameter of 0.2. This represents a deeply rough, highly jagged volatility regime.
I do have a fundamental engineering question about how they actually implemented this, though.
Sure.
If the model defines variance as a linear functional of the signature of a fractional Brownian motion, the output of that linear combination could easily dip below 0 during the gradient descent steps.
Oh, easily.
Yeah. So how do they guarantee the variance stays strictly positive during training? I mean, a negative variance would crash the entire SDE instantly.
It is a critical numerical stability problem, and the authors engineer a very elegant solution for it. Rather than feeding the raw fractional Brownian motion directly into the signature map, they apply a shifted exponential transformation to the primary process.
Okay, so they redefine the path as the initial value multiplied by the exponential of the fractional Brownian motion.
Exactly.
So the exponential function acts as an absolute floor, forcing the input to remain positive regardless of the linear combination coefficient.
Exactly. And beyond merely ensuring positivity, this transformation radically stabilizes the numerical performance of the optimizer.
It smooths out the landscape.
It does. The optimization landscape becomes dramatically smoother. By applying this specific transformation, the total computation time required for the calibration absolutely plummeted.
What kind of numbers are we talking about?
It dropped from roughly 3 hours down to just 17 to 19 minutes on a standard consumer-grade GPU.
Wait, dropping from 3 hours to under 20 minutes while operating in a 255-dimensional tensor space?
Yeah,
That is a staggering optimization achievement.
it really is. And the final accuracy metrics in the rough regime are even more impressive. In this non-Markovian environment, the signature-based approach achieved a loss of 3.5 times 10 to the negative 4.
Wow.
In fact, it actually outperformed the analytical VIX-based calibration on several specific option contracts across the surface.
It definitively proves that the rich temporal encoding provided by the signature is perfectly suited for rough fractional dynamics.
Completely. The analytical model is inherently constrained by its specific structural assumptions about the Volterra kernel.
Yeah.
But the signature framework doesn't assume anything.
It just learns the complex temporal interactions and the memory of the fractional noise directly from the data itself.
Exactly. It's beautiful.
So synthesizing all of this into a final takeaway for you, the listener. If you operate in a regime where you know your underlying market dynamics perfectly, derive the analytical approximation. The closed-form map is instantaneous, low-dimensional, and highly precise.
It remains the ultimate scalpel.
It does. But when you are dealing with unknown, complex, or deeply rough non-Markovian dynamics where parametric assumptions fail, the time-augmented signature method provides an incredibly robust alternative.
Backed by the universal approximation theorem and rough path theory, it learns the underlying volatility functional directly from the primary noise.
It trades computational simplicity for unparalleled adaptability.
It is a profound synthesis of functional analysis, rough path theory, and quantitative finance. But, dissecting this paper leaves us with a highly provocative final thought to ponder.
Oh, lay it on us.
We saw explicitly how the shuffle product inherently limits us. It mathematically requires exponentially higher tensor dimensions, specifically scaling to 2n plus 1, just to evaluate the cross terms in the correlation matrix.
Right, the 255-dimension curse for a simple level 3 model.
Exactly. So what alternative algebraic structures or nonlinear projections could we apply to the signature to compress this information?
Oh, that's interesting.
Right. Could we completely bypass the Cholesky decomposition of that Q matrix by defining a new non-Euclidean geometry for the signature feature space itself?
Wow. If we could find a way to geometrically bypass the shuffle product's dimensional explosion, the scalability and depth of rough path machine learning and quantitative finance would be practically limitless.
Exactly. It's the next great frontier for this kind of modeling.